Welcome to section 1.5 in differential equations. We are looking at first order differential equations where they look like this particular format, the derivative of y plus some function times y equals q of x. And in this particular format of first order differential equations, we are assuming that P and Q are continuous on the particular interval we are concerned with. Problems of this kind are solved by using what's called an integrating factor. And this integrating factor is rho of x equals e raised to the integral of p of x dx. What is this p of x? That's the function that's sitting here in front of the y in this particular format. So you might say, this is a strange thing. Why are you using this kind of a thing? Well, if we multiply both sides of the differential equation by this integrating factor, what happens is the left-hand side, when you look at it in the right way, is really just the derivative of your integrating factor times y. Well, if it's the derivative of this thing, then we can get our hands on it by simply integrating both sides. And so if I then divide by my integrating factor, we figure out what y is, and y then is 1 over rho of x times this particular interval. And so in practice, it's not too bad. When we look at some application problems, it can become complicated. So let's take a look. In question 1 here, we have y prime plus 8y equals 1. We have an initial condition, y at 0 is 1. So it's already in a good format. Y prime plus p of x equals q of x. So p of x is 8. The integral of 8 is 8x. Don't worry about the arbitrary constant. And so my integrating factor is e raised to that, so that becomes e to the 8x. So I take my integrating factor, multiply it by both sides of the differential equation. The left side becomes the derivative of the integrating factor times y. All right, so to get rid of the derivative, we're going to integrate both sides. All right, so if I integrate the left, I get e to the 8x times y. Integrate e to the 8x, we use integration by substitution. U is 8x. So I pick up a constant of 1/8. To get y by itself, divide both sides by e to the 8x. And then just simply distribute. So if I distribute this in, the e to the 8x cancels. And I get c e to the minus 8x because it's in the denominator. And so if we now use our initial condition that y at 0 is 1, so plug in 0 for x here. E to the 0 is 1, so I get 1 equals 1/8 plus c. And so solving for c, we get that c is 7/8. And if you plug that into our problem, you'll see this particular format. What could I say about this format? Well, if I look at the limit as x goes to infinity, this particular item will decay to 0, which means our y of x is going to be leveling off to 1/8. In question 2, we have xy prime plus 3y equals 4x. We have y at 2 is equal to 7. So the 2 is important, and you're going to see why in just a moment. All right, so looking at it in this format, that's not what we need. So I divide both sides by x all the way through. And so finally, I do get it into a format that looks like what we're going to be able to use our integrating factor on. So q of x is 4. That's continuous everywhere. P of x is 3 over x, and it's continuous on its domain, which is everywhere except 0, which is fine, because we're trying to solve this starting off at 2. So we clearly have continuous P, continuous Q in the spot we're looking for. All right, so P of x is 3 over x. Integrate that, and I get 3 ln absolute value of x. So my integrating factor is e raised to that item. Now we've used this previously. I need e to be e ln of something. I can't have that 3 in the front. So by the properties of logarithms, push it back up as an exponent. And now I have e ln of this item cubed. And so because e and ln are inverse functions, I get x cubed back. All right, so I'm going to multiply both sides by my integrating factor, which is x cubed. Integrate both sides, so I'm integrating 4x cubed, which is easy. That's 4x to the 4th over 4 plus c. All right, cleaning it up, I need to get y by itself, so I divide by x cubed all the way through. So this gives me an x. I get cx to the minus 3. But we're focusing on y at 2 is supposed to be 7. So plug in 2 for x, 2 for x. 2 to the minus 3 would be 1/8. So I get c over 8 is equal to 5. And so c is 40. And so we get our solution for y of x. And this is basically valid when? Well, my initial condition was at 2, so greater than or equal to 2. All right, in question 3, we have a similar situation, xy prime minus y equals x. We are starting this at 1. All right, so we need to clean it up first, dividing through by x to put it in a format where I've got q of x is 1, p of x is minus 1 over x, and so this is going to be valid for x bigger than 0. All right, so integrating 1 over x, I get minus ln absolute value of x. I've got e raised to that for my integrating factor. Can't leave the minus 1 there. It must move out into the top. And so e to the ln of this item is simply 1 over x. So I'm going to multiply that by everything in the problem. All right, well, remember the right-hand side was a 1, so I just get 1 over x. Integrate both sides. All right, we're rolling here. And so I get 1 over x y ln absolute value of x plus c. Multiply through by x. And so I get x ln absolute value of x plus cx. But we're doing this when x is bigger than 0. All right, so I don't need the absolute values. Y at 1 is 3, so plug in 1. But ln of 1 is 0, and so I figure out that C is 3. In question 4, all right, we have our first order problem. We have y at 2 pi is equal to 0. So as before, I need to clean all this up. I'm also noticing that the y is on the wrong side of the equals. It needs to be on the left for me to identify p of x. All right, so dividing through by x. All right, over here on the right, I get an x to the 9th cosine of x. On the left, all right, here's my p of x. Again, is going to be valid for x bigger than 0. All right, integrate this. We've done several times now already. I have e to the integral of p. Can't leave the minus 9, must push it back up. And so I get e to the ln absolute value of this item, and I get absolute value of x to the minus 9. But we're doing this for x's bigger than 0, so I get a 1 over x to the 9. Multiply both sides by that item. All right. On the right, the x to the 9ths cancel, so I'm simply integrating the cosine, and I get the sine. So, multiplying through by x to the 9th, we get our general form. Let's see, y at 2 pi was 0. All right, so plug in 2 pi in all the places we have an x. But the sine of 2 pi is 0, so that whole term is gone. I don't need to multiply this out because c times it is 0, which says that c is 0. So this term is gone, and so we get y of x is x to the 9th sine of x. And so for x greater than 0, notice I get a sine, but its amplitude is growing quickly as x goes to the right forever. All right, question 5, we have an application problem, a common problem with salt and tanks and mixing, but it is not easy. So let's talk about this. I've got a tank. Here's my tank. The tank has, at time 0, 50 gallons of pure water. Okay, so at time 0. I've got a salt water solution coming in. It's coming into the tank at 2 gallons per minute. And the concentration in this water that's coming in is 5 pounds of salt per gallon. The I notation is for the inputs. If you see the O notation, that's for the outputs. The tank is letting this solution out, and it's coming out at 3 gallons per minute. The concentration is, I don't know, but the rate is 3 gallons per minute. All right, so what can I say? Input flow is 2, output flow is 3. So the net flow is 1 gallon per minute out. So notice the output is bigger than the input, so the tank will go dry. Okay, so initially there's 50 gallons. It starts coming out, and eventually the tank will be empty. All right, so if I look at that situation, We start off at 50 gallons. The amount of volume at any time is 50 minus T. Why that? Well, remember, my net flow is 1 gallon per minute out. So that's why it's 50 minus 1T. So after 50 minutes, the tank will be dry. All right, let's see. Initially, the tank had pure water in it. All right, so X of T is the amount of salt in the water at any particular time. All right, so let's see. What do we have here? We've got our differential equation for this solution. Also, let me point out something else that's important before we go on. Scrolling back up. This tank is perfectly mixed. Even though there's not a picture in here, picture a stirrer that's moving quickly and stirring the tank. So because it's perfectly stirred, this is an ordinary differential equation. If there was no stirring in the tank, then you would have diffusion going on, and you now have a partial differential equation. All right, so back to my basic model for this. I've got the rate of the input, concentration of the input, minus the rate of the output. And what is this V on the bottom with the X here? Well, X over V is the concentration coming out. All right, so let's see, what do I know? Well, first off, this stuff has got to come to the left. All right, my rate out was 3. The concentration in there at that time is X over 50 minus T. The right-hand side is RICI, which was 2 and 5, so 10. And so that sets up our basic differential equation for X of T, which is the amount of salt in the tank, basically from 0 up to 50 minutes. All right, so P of T is here. We need to integrate that. That's going to be integration by substitution. So you let U be the bottom, and you're going to get a minus out, so minus ln absolute value. But we know I need to take e to this thing, so I'm going to push the minus 3 back up. All right, so I get e to the ln of this item, and so this is my integrating factor. All right, so rho of t is 1 over this item because it's to the minus 3. Multiply both sides by the integrating factor. Now I'm going to integrate both sides. Left is easy. On the right, pull the 10 out in the front. I'm going to need to use integration by substitution again. So I'm going to get a u to the minus 3. So minus 3 plus 1 is minus 2. I pick up a minus in the front. I've got a minus underneath, and so that would make a positive 5. I need to multiply this item by both sides to get x of t alone. All right, now we have a bit of cleaning to do. I've got this term to the third, this term to the minus 2. So that gives me a power of 1. Distributing in the 5. On the right, I can distribute a little bit in. And so we are to this point, but at time 0, the amount of salt in the tank was 0. It was pure water. So when t equals 0, that's 0. This part is going to be 50 cubed times c. And so finally, solving for c, we get minus 1 over 500. All right, so this is my basic relationship for the amount of salt in this particular tank from time 0 up until the tank is dry at 50 minutes. All right, so looking at a graph for this, at time 0, we had no salt in there. At time 50, there's no salt because it's empty. During that time, we're going to have a particular time of maximum salt. All right, so on this curve, it's going to be here at the peak, and the peak is when the first derivative would be 0, looking for critical points. All right, so the derivative of 250 is 0. Derivative of minus 5t is minus 5. The derivative of this term is going to be a chain rule. And so I need to solve when is this thing 0. So with a bit of grinding and cleaning, we finally get this thing down to a quadratic equation to solve. So you can solve it with the quadratic formula. You can use some online tools to calculate this item. And it turns out there are two times, 21.132 and 78.168. Now I can throw that one away because we know the tank is empty at 50 minutes, and that's beyond the time. So the time for maximum salt in the tank is at about 21 minutes. So plug that into my formula for the amount of salt, and we get about 96.23 pounds of salt in the tank at 21.132 minutes. All right, now if that wasn't hard enough, we now have, in our next question, two tanks that are being cascaded together. So let's see what's going on here. I've got pure water coming into tank 1. Tank 1 initially has 200 gallons of pure ethanol. All right, got that. We have 20 gallons coming in, 20 gallons going out. So the rate is going to stay the same. And the rate it's leaving tank 2 is 20 gallons per minute. So, what else? Initially, tank 2 had 200 gallons of pure water. Okay, so pure ethanol in tank 1, pure water in tank 2, pure water is coming into tank 1. Okay, so tank 1, which had ethanol, is going to begin to get diluted. But this ethanol mixture is coming out into tank 2, adding more ethanol to tank 2. So, X of t is the amount of ethanol in tank 1 at time t. Y of t is the amount of ethanol in tank 2. All right, so let's see. For tank 1, we have our basic differential equation for mixing. All right, so rates in, rates out. My rates in were 20 gallons per minute in. Pure water, All right, so that's 0. The rate coming out, well, 20 gallons per minute. The concentration is, well, whatever's in there divided by the initial amount of 200. That 200 is staying stable. It's not changing. Why? It's not changing because we've got 20 gallons in, 20 gallons out. So we're not leaking, we're not adding, we are maintaining the original 200 gallons. All right, so that's 0. I get a fairly simple differential equation to solve. I can solve it by separation. All right, so left-hand side, ln absolute value of x equals that. Take e of both sides. And so we get a basic formula for the amount in tank 1. And initially we had at time 0, 200 gallons of pure ethanol in there. All right, so there's my solution for tank 1. What about for tank 2? All right, well, the inlet coming into tank 2, the rate was 20 gallons a minute. The concentration is coming from x of t because it was being dumped in. So here's my x of t divided by the volume in tank 2 minus, now what about the outputs? Well, 20 gallons coming out. Concentration is y divided by 200. Again, the volume in tank 2 is staying the same because 20 gallons in, 20 gallons out. All right, so cleaning things up, 20 into 200, 10 times. X of t is this number. And so cleaning that up, I have this minus 1/10 y. And so now if we manipulate this, we get our first order problem where P of t is 1/10, Q of t is this 20 e to the minus t over 10. So I need to get my integrating factor, so e to the integral P of t. All right. Multiply both sides by the integrating factor. Integrate both sides. All right, so let's see. Integrate the left is easy. On the right, notice this e to the 1/10 t perfectly cancels this term. So I'm simply integrating 20. So I get 20t plus c. Multiplying through by e to the minus 1/10 t. All right. Y at 0. All right. This was the amount of ethanol at time 0. But remember, tank 2 had pure water, so C is 0. So I get this relationship for y of t, the amount of ethanol in the tank at time bigger than 0. All right, so if I look at a graph of all this, let's see if I can get my whole graph on there, almost. So x of t was the concentration or the amount of ethanol in tank 1. So starts off at 200, is decreasing. The amount of ethanol in tank 1 is growing because more ethanol is coming in. But remember, both of these are decreasing because initially pure water is going into tank 1. So tank 1 is going to get more and more diluted. So tank 2, y of t, is going to have a maximum. That's when y prime is 0. So I find y prime, try to set this equal to 0. This exponential is never 0. So the only thing that could be 0 is this part, and that happens when t is 10. So plug in 10, and that's going to occur at 73.58 gallons. So as we've seen previously, the basic mechanics are fairly easy, but as soon as we get to an application, things become really complex.